Now we are at our last topic, topic 4, and I'm very glad that you're still with us. And I think this is a topic which will be very interesting for you. I will move myself out of the picture, and I hope I have done that right. Yep, so let's start with energy losses in buildings. And that's quite interesting because we will talk about different ways of that. But let's focus first on the energy losses done by transmission. So these are the four gray areas, green arrows. So windows, roof, wall, and the ceiling. Altogether, roughly 60% energy losses there. Then we have ventilation, also infiltration. So ventilation is when you really want to do it, getting fresh air in, and infiltration is more when you don't want it. And then we have building service, which is, for example, the loss of unused heat through the chimney and so on. So transmission, we will focus on thermal conductivity, the U value, and the thermal bridges. I think it's one of the most important uh, uh, um, topics right now for this unit here, for this topic. And then we have ventilation, which will be, I think, the third presentation, and then we will focus on building service. But first, we have to know about transmission losses, and for that, we need the thermal conductivity. So we have Dämmstoff, which is German, and in English it's insulation. I was choosing EPS, the expanded polystyrene, 0.040 lambda. So if you have 2 centimeter of that insulation material, it's like the same thermal conductivity like a full concrete massive concrete by, that would be the density, the lambda 2.1. So you can see how much material you would use to receive the same thermal, thermal conductivity. So what is thermal conductivity? It is a steady state heat flux through a unit thickness of homogeneous material and so on and so on. I believe that to you because we not really need how it is calculated. You would need the units and to know what it is. The calculation is already done by other people, and you normally can find that in tables like this one, for example. You have here the EPS 0.441 as conductivity and some other units which are also important for the assessment of materials and if they are uh, good for the purpose which they are aiming for. So we also need the thermal conductivity to actually calculate the U value, which is the main focus on that uh, lecture now. So what is the U value? It's a thermal transmissions of building envelope. So we again on our 4 arrows here, roof, window, floor plate, and wall. And we will not directly calculate a U value because we have software for that, and that is not the the purpose of that module 1 and 2. But what I want to show you is how, for example, is done by Edge, and that will be one of the following slides. So as I said, we will not go in deep into that one. That's a formula, and it can be very, very long depending on how many layers of material you have for your wall, roof, or for a floor plate. But in a nutshell, and the very simple one, for example, you have a brick wall, you have a outer mortar layer and an inner one, and roughly the U value would be 1.63 watt per square meter per Kelvin. If you add some insulation here, for example, 12 centimeter, then it will go down on 0.25 watts per square meter Kelvin. So let's go a little bit deeper into that. We have a wall here, just regular brick wall, 1.8 U value, then with an insulation of 8 centimeter, and then with a, depending how big we make how large we make the insulation, 16 to 32 centimeter. I think you remember the first slide where we were talking about transmission losses. As thicker the insulation is, as less transmission losses we have. So I think that is a very important to remember that. As lower the U value, as less is the heat transfer. And that's what we really want to achieve when we are designing a building. Best practice would be, for example, a passive house. So how is the U value calculation done? So we are using Edge, and that's Edge is excellence in design and great efficiency. The next presentation will be focusing on Edge and what Edge is. I just want to show you that you don't have to calculate U value. You just put your materials and the thickness of the materials. The conductivity is already given. As soon as you put the material there, how your wall is built up, then it will come up here with the conductivity value, and you give the thickness. And then here, for example, the plaster, it was 1 millimeter on one side, 1 millimeter on the other side, so 2 millimeters. Altogether, you have a 42 millimeter thick wall and with a U value of 0.1. That was a wall which we were building, or building which we were building in the Philippines. And you also have to give the surface area of the wall, and then you jump to the next wall, and then you jump to the roof, and then you jump to the window, and you just fill in the gaps. And that's actually quite an easy way. That's why Edge is actually my favorite calculation tool for green building standards and for U value. So that's so much to Edge. Let's go on an underestimated value, which is the thermal bridges. So heat makes its way from the heated space towards the outside. In doing so, it follows the path of the last or least resistance. Thermal bridges are also called cold bridges, and that's most of the time because if you're inside the building and if you touch an area which is colder than another area, you can feel it's colder, so you say cold bridges. But if you would be on the outer side, like on the building on the outer side, if you would touch this one, that would be warmer. So why are cold bridges thermal bridges, cold bridges are important? Because they can increase moisture penetration in the building material, which could lead to some damage in the building structure. It also can lead to mold growth and to a bad indoor environment. Of course, if the heat can transfer easily, we have heat losses, and that will we have to increase heating. Best seen thermal bridges are by thermography. So you can see some pictures here. Let's go through them step by step. Here, for example, we have a balcony concrete plate. You can see here we have some heat transfer, very visible, because the rest of the building is well insulated, where you can see it's blue, but where it's reddish, it's already a heat loss there. Typical thermal bridge. Also typical thermal bridge are these two lines here. These are the weak insulation at floor slabs or ceiling. Also a typical one here, the bridges, the stairs downstairs, in the cellar or up there, no thermal separation of building elements. For example, here the staircase, you can see how the heat from the inner building is actually transferred to the outer wall here where the stairs are. Another one is here, this area under the connection between roof and wall. So you also, as you can see, there is some heat energy losses there. Then here are areas of the radiators under the window. It's also a typical heat loss area, not well insulated here. And as it is also in my apartment, the window steel, they are quite cold in the winter time because they are not well installed, and I think it's one plate going underneath the window, so it's pretty cold there. And here with the thermal graphy, you also can see invisible damages. Here, for example, wet insulation material under the roof. Here you can see where the heat is. So this is a useless insulation there. So, and the last slide is indicating, for example, how it is calculated, the thermal bridge heat losses. So you have all the different kind of materials. So external wall, you have the U value, you have the area, and then you calculate them all together. And but for the heat bridges, sometimes they're not visible and you see them not very well, and the calculation takes quite a time. So it's actually commonly used that the thermal bridges heat losses are just added to the total heat transmitting losses by 10%. As you can see here clearly, that is how it's done. Of course, you can calculate, but you need the time for that. And so that is the end of part 1. And the next one will be an edge presentation, a presentation on edge. Thank you very much for listening.